This video is going to continue the discussion of moving from acceleration to velocity to position through the process of adding up small changes. As we saw previously, change in velocity is acceleration times change in time. In other words, acceleration is the slope of the velocity versus time diagram. And likewise, change in position is velocity times small change in time. In other words, velocity is the slope, rise over run, of the position versus time diagram. We've also introduced the idea that to get a big change, a finite change, what you should do is accumulate and add up or bring together, integrate all of the small changes. So we write that the total change in velocity, the big change in velocity, which can of course be written always as the final velocity minus the initial velocity, is the accumulation, the integration, the addition of small changes in velocity from the initial velocity to the final velocity, or written alternatively, since small changes in velocity are accelerations times small changes in time, acceleration times small steps in time. The variable which we're stepping over now, the so-called integration variable, is time rather than velocity. We've got to put our endpoints, our starting and our ending, at the corresponding values for time. We started at time 0. We went to time t. We started at the velocity at time 0 and went to the final velocity at time t. The corresponding set of relationships for changes in position would say that the big change in position, in other words, the final position minus the initial position, is just the accumulation of small changes in position from your starting point to your ending point, which, since small changes in position are velocities times small steps in time, can alternatively be written as this integration, this accumulation, from the corresponding values of the integration variable here, which is time, the initial time being 0, and the final time being t. Now, these equations which we have written have a very beautiful graphical interpretation, which is what we want to talk about for the remainder of this video. The graphical interpretation. We talked previously about the graphical interpretation going the other direction of slopes. Velocity is the slope of the position graph. Acceleration is the slope of the velocity graph. But there's also a graphical interpretation which leads us from acceleration to velocity to position. If we have a velocity plot as a function of time, and we have some curve like that, the velocity is the height of that plot, and we're going to take little steps in time, each of which has a width equal to the infinitesimal width. We've drawn it wide so that we can see it. Remember, d always means in the limit getting very, very small, infinitesimal, in the limit tending to 0. So let's see what our distance traveled looks like. Our distance traveled is the accumulation of heights, velocity, versus widths, step in time. We call that an area. Now, velocity is measured in meters per second, and time is measured in seconds. It's an area in the sense that it's a height times a width, but it's not an area in the sense that it's meters squared. It's whatever the dimension of the height is times whatever the dimension of the width is. Since the height here was meters per second, and the width was second, meters per seconds times seconds gives us meters. In fact, this is telling us that the height times the width, the little bit of area underneath the velocity versus time graph, corresponds to a distance traveled. Velocity times little step in time, that little bit of area is a distance traveled. That's another little distance traveled. That's another little distance traveled. If the velocity is higher, in that tick of the clock, you travel a greater distance. If the velocity is lower in that tick of the clock, you get a smaller area and you travel a smaller distance. If the velocity is negative, then in that tick of the clock, you have the area under the curve below the axis. It's a negative area. In that case, you traveled backwards. And if you have a negative velocity that you allow to act over some period of time, it moves you backwards. So this equation, written in English, says change in position is area under the velocity versus time plot. Correspondingly, exactly the same thing. This equation says that changes in velocity are height times width, areas under the acceleration versus time plot. So we learn to work in one direction by taking slopes. Velocity is the slope of position. Acceleration is the slope of velocity. If we want to go the other way, from acceleration to velocity to position, changes in velocity are added up areas with height, acceleration, and width, step in time, the area under the acceleration versus time curve. Correspondingly, changes in position are given by the area under the velocity versus time curve. Let's write that as well. Up at the top here, change in velocity is area under the acceleration versus time. That's what this equation says. And change in position is area under the velocity versus time plot, is what this equation says.